Hey y'all, in today's video, we're going to learn how to calculate the voltage of a non-standard cell. Let's go ahead and get started. In the last video, we talked about non-standard cells, also known as concentration cells. These are going to be batteries where it's a spontaneous process, but the voltage isn't going to be equal to what you would have expected if all the concentrations were 1 molar. Today, we're going to look at a little bit more in depth the quantitative component. So not just like, would you expect a greater voltage or lesser voltage, but we're going to talk a little bit more about why you would expect a greater voltage or less voltage. And in the end, it comes back to equilibrium. If you remember from equilibrium, all of our questions came back to a Q versus K comparison. In this unit, it's a little bit different. In this unit, we're not so much comparing Q to K, because remember, K is always going to be greater than Q in a functional battery. In fact, in a battery that stops working, that's when its Q is equal to K. So we are always going to be a Q less than K so long as our battery is functional. Our question in this unit is going to be comparing Q to 1. So when Q is equal to 1, we are at standard conditions. When Q is equal to 1, it's because all concentrations are 1 molar or equivalent to. So the question is not, are we comparing Q to K? It's, how do we compare Q to 1? Q cannot be greater than K in a battery. Remember, a battery that's functional is always going to be spontaneous. When Q is greater than K, we end up with a process that would favor the reverse. Well, that's not a functional battery. Going in the reverse is not functionally going to make your battery spontaneous in the forward direction. It's the opposite. So in a functional battery, Q is always less than K. So what we're comparing Q to is 1. The reason we're comparing it to 1 is because it is a standard cell, a standard battery. The voltage is going to be when the concentrations of your ions are each equal to 1 molar concentration. And if I look at the Q calculation here, 1 over 1 is 1. And it doesn't even matter what your K value is relative to your Q in that situation. It's all about whether the Q is greater than or less than 1. So if you want to think about it in this way, the closer our Q value gets to K, the closer our voltage gets to 0. So voltage is going to decrease as a chemical reaction is going to continue, because what's going to happen is our Q value is going to get bigger as we create more products. Our K is always positive. So as our Q gets bigger, it's always getting closer to K. What that means is that the Q value is going to grow because you're creating products and you're using reactants. Your numerator gets bigger, your denominator gets smaller. So your Q value grows over time. As that happens, our voltage decreases. Specifically, there's an equation that tells us why that is. This is called the Nernst equation. So let's talk about the Nernst equation. The Nernst equation is on your formula sheet, but I will tell you right now, you're never going to have to actually calculate the E of cell based on the Nernst equation. But let me talk to you really quickly about what this equation shows. On the left side of the equal sign, the Nernst equation is showing E of cell, but you'll notice that this E of cell does not have the degree sign on it. This is telling us this is the voltage we would see. If we tested this battery, that's the voltage that I'm getting. That is equal to E naught cell, which would be the voltage of the cell at standard conditions. So if I look at a table and I take the E of oxidation and E of reduction of my reactants and I use them, that's the E that I'm calculating from those standard E values. That's the E at standard conditions, 1 molar concentrations. Then I take that value and I subtract this mess of numbers. Now, this mess of numbers, again, because we're not using quantitative calculations here, we're using qualitative here, is a way of essentially calculating the E change, the change in voltage as a result of the Q value. This mess of numbers here includes the gas constant, but used in a slightly different way, negative 8.314 in this case. It includes the Faraday's constant, 96,485 coulombs per mole of electrons. It includes N, which is moles of electrons transferred over the course of this chemical reaction. And it includes temperature in Kelvin. So here's this mess of numbers that really you're not going to use in your calculations, but I just wanted you to be familiar with what each of the variables represented. The kicker here is that it's natural log of Q. And we're subtracting this mess. So if you remember natural log of 1 is 0. So if my Q is equal to 1, this whole mess, this whole term is 0, which means E of cell that I see and E of cell standard conditions are equal. When Q is not equal to 1 is when we start to see some changing. Think about it this way. If Q is greater than 1, that means that whole term is going to be positive, and we're subtracting that number. Natural log of a value greater than 1 is a positive number. So we're subtracting a positive number from your E of cell. So when Q is greater than 1, the overall voltage that I see is less than it would have been at standard conditions. If Q is less than 1, natural log of a number less than 1 is negative. So I'm subtracting a negative, which means the E that I see is greater than it would have been at standard conditions. Let me remind you one more time. You're not quantitatively finding the new voltages by requirement. However, they give you the Nernst equation on the formula sheet. You know how to find Q. You could find the voltage of a cell at any condition with this information. You can use it as a justification, but you don't have to actually get a numerical value out of it. So let's do an example here where we're using the Nernst equation to predict the change in voltage of a concentration cell. Here I've got a zinc copper cell, and instead of standard conditions, here I have the zinc concentration is 2 molar and the copper concentration is 0.5 molar. What I need you to do is set up the equation using the E of reduction values, predict what's going to be oxidized and reduced. Then, using what we know about Q in the Nernst equation, predict what the change in voltage would be. If you want, go ahead and calculate the new voltage. Take a second, look over it, do the calculations, and come back when you're ready. Okay. So if we look at this process, we see that the zinc is being oxidized and the copper is being reduced. That means that the Q value is going to equal the concentration of zinc divided by the concentration of copper ions. So the concentration of zinc goes from 1 to 2, so it's 2 over the concentration of copper, which is 0.5. That means my Q value is equal to 4. 4 is greater than 1, which means that the natural log of 4 is going to be a positive number. So I'm subtracting a positive number from my standard voltage. Therefore, my voltage is going to be smaller at these conditions than they would have been at standard conditions. Now, one thing to be aware of with the Nernst equation and Q values here is that it is actually dependent on stoichiometry. If, in this case, we have a 1-to-1 ratio, it doesn't matter if we had concentrations of 2 over 2 or 4 over 4 because the Q wouldn't change. But if we were in a situation where maybe it wasn't a 1-to-1 ratio between the two ions, maybe it was a 2-to-3 ratio or a 1-to-2 ratio, now all of a sudden, changing concentrations can change the Q value differently than it would have if it was a 1-to-1 ratio. So be careful with that. Be careful with that. It's not common and you're not often going to see it, but you could see it. And that's a great way to kind of trip you up in this type of a problem. So that wraps up today's video. Let's do a quick recap. Today, we learned how to use the Nernst equation to be able to predict the change in voltage of a concentration cell. Keep in mind, you're not going to necessarily have to find a number, but you can use the Nernst equation to justify the change in voltage when you're answering a question. It is on your formula sheet. It's present and available to you. So if you wanted to use it to calculate the voltage, you could do that. The key to the Nernst equation is you're comparing Q to 1. If Q is greater than 1, or if Q is less than 1, our voltage will be different than that at standard conditions, and you need to be able to predict that. Today's video was written, directed, produced, and edited by Isaac Chan and Jasper Shu. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.